In real-world engineering, many structures are intentionally designed as statically indeterminate. Why? Because redundancy improves safety and serviceability. If one member fails, loads can redistribute to others. However, this redundancy means that equilibrium equations alone are insufficient. We need deformation compatibility and material behavior laws. 2. The force method of analysis. The force method, also known as the flexibility method, starts by releasing enough redundancies to make the structure determinate, then reapplying them while ensuring compatibility of deformations. Steps. Identify redundancies. Remove redundancies to form a basic determinate structure. Apply unit loads at the location of redundancies. Calculate displacements due to actual loads and unit loads. Solve for redundancies using compatibility equations. 3. Displacement method of analysis. While the force method focuses on unknown forces, displacement methods focus on unknown displacements. Key displacement methods. Slope deflection method relates member end moments to rotations and translations at the ends. Moment distribution method, an iterative approach that distributes moments through the structure until equilibrium is achieved. Stiffness method, the foundation for modern computer-based structural analysis. It formulates relationships between nodal forces and nodal displacements. 4. Introduction to the stiffness method. The stiffness method involves defining a stiffness matrix for each element, assembling the global stiffness matrix, applying boundary conditions, solving for nodal displacements, then calculating member forces. This is the core principle behind most structural analysis software. 5. Introduction to finite element modeling. Finite element modeling, FEM, is a numerical method that breaks structures into smaller elements connected at nodes. Process. Discretization, dividing the structure into finite elements. Selection of element type, truss, beam, shell, or solid elements. Formulating element stiffness equations. Assembling into the global stiffness matrix. Applying loads and solving. FEM allows analysis of very complex structures and load conditions. 6. Plastic analysis. While elastic analysis assumes structures remain within the elastic range, plastic analysis considers the ability of structures to undergo plastic deformation before collapse. Plastic analysis is particularly important for steel design, where ductility allows redistribution of moments. 2 main approaches. Plastic hinge method. Collapse occurs when sufficient plastic hinges form to create a mechanism. Upper and lower bound theorems provide safe estimates of collapse loads. 7. Practical applications in structural engineering. In professional practice, analysis must consider load combinations prescribed by codes, material properties and nonlinearities, dynamic effects such as wind gust and seismic events, constructability and safety factors. Structural mechanics is not just about solving equations, it's about designing safe, economical, and buildable structures. 8. Summary of Module 2. In Module 2, we progressed into indeterminate structures, learning force and displacement methods, the slope deflection, moment distribution, and stiffness methods, the basics of finite element modeling, the principles of plastic analysis. Together, Modules 1 and 2 give you a comprehensive understanding of structural mechanics from basic determinate analysis to advanced computational methods.